At 2:14 a.m. on January 17, 1934, chemical engineer Harold Westbrook stood in the basement of Chicago's Palmer House Hotel, watching 40 gallons of his experimental antifreeze solution drain into a burst pipe that had already flooded 3 floors. The hotel manager had called him insane. The plumbing contractor had threatened to sue. Every chemist at Standard Oil, where Westbrook worked, had told him the formula would corrode the pipes within a month. But Westbrook had done the math. Water froze at 32 Feb. His solution stayed liquid at -40 Feb. And if it worked, it would end a problem that had plagued northern cities since the invention of indoor plumbing. Burst pipes. Every winter, hundreds of thousands of them. This is the story of how one man's insane solution saved billions of dollars in property damage and changed winter forever. Chicago in January 1934 was 22 degrees below zero, the coldest winter in 40 years. Pipes were bursting everywhere. The Palmer House alone had suffered 17 pipe failures in 3 weeks. Each burst meant flooding, water damage, repair costs, guest evacuations. The hotel was losing $3,000 per day. Multiply that across every building in Chicago: homes, hospitals, factories, schools, and the city was hemorrhaging money. The problem was simple physics. Water expands when it freezes. A closed pipe filled with water has nowhere for that expansion to go. The ice builds pressure. Pressure cracks the pipe. The pipe bursts. Flooding follows. The traditional solution was heat. Keep the pipes warm enough that water never froze. Building codes required pipes to run through heated spaces, away from exterior walls. Insulation wrapped every exposed section. Heat tape provided backup warming in critical areas. But heat was expensive. Coal furnaces ran 24 hours during winter. Heat tape drew constant electricity, and if power failed, if furnaces went out, if temperatures dropped too fast, pipes froze anyway. Chicago's infrastructure couldn't keep up with the cold. The city needed a different approach. It needed chemical intervention. Antifreeze wasn't new in 1934. Ethylene glycol had been used in automobile radiators since 1926. The principle was straightforward. Mix water with a chemical that has a lower freezing point, and the mixture freezes at a lower temperature than pure water. Car engines stayed liquid at temperatures that would freeze plain water solid, but automotive antifreeze was toxic. Ethylene glycol was poisonous. You couldn't put it in drinking water pipes. Building codes explicitly forbade it. Any chemical solution for plumbing had to be non-toxic, non-corrosive, and cheap enough for mass adoption. That combination didn't exist. Westbrook had been working on the problem for 2 years. He was 34 years old, chemical engineer from MIT, employed by Standard Oil's research division in Indiana. His official job was developing petroleum additives for cold weather performance. His unofficial obsession was solving the frozen pipe crisis. He'd grown up in Minnesota, knew firsthand the devastation of burst pipes. His family's farmhouse had flooded twice before he turned 12. His mother had lost her wedding china to water damage in 1911. Westbrook remembered watching his father try to thaw frozen pipes with a blowtorch, remembered the moment the pipe burst and scalding water sprayed across the basement. His father had been hospitalized for second-degree burns. That memory drove Westbrook's research. The challenge was finding a chemical that met all requirements. It had to lower water's freezing point significantly, at least to 0 FF, preferably lower. It had to be non-toxic enough for drinking water systems. It had to be non-corrosive to iron, copper, lead, and galvanized steel pipes. It had to be stable across temperature ranges from -40 FF to 160 FF, and it had to be chemically inert enough that it wouldn't react with chlorine, fluoride, or other water treatment chemicals. Every substance Westbrook tested failed at least one requirement. Propylene glycol was non-toxic but expensive. Calcium chloride was cheap but corrosive. Alcohol-based solutions evaporated. Sugar-based solutions bred bacteria. Salt solutions corroded metal. Westbrook had tested 147 different formulations by December 1933. None worked. His supervisor at Standard Oil suggested he abandon the project. There was no commercial market, no potential for profit. The company needed him focused on gasoline additives, not plumbing fantasies. Westbrook ignored him. He was close. He could feel it. The breakthrough came on December 28, 1933. Westbrook was reviewing a chemistry journal article about glycerol production from soap manufacturing. Glycerol, also called glycerin, was a byproduct of soap making, produced in huge quantities and often discarded. It was non-toxic, had been used in food and medicine for decades. Its freezing point was 64 F higher than water. But the article mentioned that glycerol solutions exhibited unusual freezing point depression characteristics that didn't follow standard calculations. Westbrook requested samples immediately. He spent the next week testing glycerol water mixtures. Pure glycerol froze at 64 F. A 50-50 mixture with water should freeze around 48 F, based on standard calculations. It didn't. It stayed liquid down to 15 F. Westbrook increased the glycerol concentration. 60% glycerol, 40% water. Liquid to 0 FF. 70% glycerol, 30% water. Liquid to -10 F. The depression wasn't linear. It was exponential. At 75% glycerol concentration, the mixture remained liquid at -40 FF. And glycerol was non-toxic, non-corrosive, chemically stable, and cheap because soap manufacturers were paying to dispose of it. Westbrook had his solution. He mixed 400 gallons using industrial glycerol, purchased from a soap factory in Gary, Indiana. Cost $23 for materials. He needed a test site, a building with extensive plumbing, preferably one already suffering freeze damage. He contacted every hotel in Chicago, offering free freeze protection in exchange for test access. 17 hotels refused. The 18th, the Palmer House, agreed. Their plumbing was failing catastrophically. They were desperate. On January 15, 1934, Westbrook's crew arrived with 400 gallons of glycerol solution and a plan that violated every plumbing code in Illinois. They would drain the building's water system, refill it with 75% glycerol solution, and leave it exposed to freezing temperatures. The hotel's chief engineer, Marcus Donnelly, said it was insane. The solution would corrode the pipes. It would contaminate drinking water. It would create health hazards. The city building inspector agreed. Westbrook was not permitted to proceed. He proceeded anyway. Donnelly ordered him off the property. Westbrook convinced the hotel manager to override Donnelly by offering a $10,000 insurance bond against damage. The manager agreed. Donnelly resigned in protest. They started draining the system at 8 p.m. on January 16th. The Palmer House had 847 guest rooms, 63 bathrooms, 2 kitchens, and a laundry facility. The total pipe network held approximately 8,000 gallons of water. Draining took 6 hours. Refilling with glycerol solution took another 4 hours. By 6 a.m. on January 17th, every pipe in the building was filled with Westbrook's formula. The temperature outside was -18 FF. Interior temperature in unheated pipe chases was measured at -4 FF. Water would have frozen solid hours ago. Westbrook's solution remained liquid. Then, at 2:14 a.m. on the morning of January 17th, a pipe burst in the basement. Not from freezing, from water hammer. A maintenance worker had opened a valve too quickly. 40 gallons of glycerol solution flooded the mechanical room. The hotel manager was furious. The solution was working, but one failure was enough to condemn the project. Westbrook spent the next hour examining the burst pipe. It hadn't corroded. It hadn't been damaged by the glycerol. It had failed due to mechanical stress completely unrelated to the chemical treatment. He explained this to the manager. The manager didn't care. He wanted Westbrook gone. He wanted the building drained and returned to normal operation. Westbrook asked for 48 more hours. The manager refused. Westbrook increased his insurance bond to $25,000. The manager agreed to 24 hours. January 18th was minus 26 FF, the coldest day of the winter. Across Chicago, pipes burst in 3,400 buildings. The Palmer House, filled with glycerol solution, had 0 freeze failures, not one. By noon, word had spread. Hotel managers from across the city called requesting information. Westbrook spent the afternoon fielding calls. By evening, he had commitments from 11 more hotels to test the system. By the end of January, he had 47 buildings using glycerol antifreeze. The results were undeniable. Buildings using Westbrook's solution reported 0 freeze-related pipe failures during the winter of 1934. Control buildings, those using traditional heat-only protection, reported an average of 8.3 freeze failures per building. Insurance companies noticed. Property damage claims in treated buildings dropped 94% compared to previous winters. The numbers proved the concept worked, but commercialization required regulatory approval, and Chicago's building codes explicitly prohibited antifreeze in drinking water systems. Westbrook spent February 1934 fighting bureaucracy. He presented data to the city building department. They rejected it. Too small a sample size, they said. He presented laboratory analysis showing glycerol's non-toxicity. They questioned the methodology. He presented endorsements from 11 hotel managers, whose buildings had survived the coldest winter in 40 years without a single burst pipe. The building department remained unconvinced. They wanted long-term corrosion studies. They wanted health department approval. They wanted insurance liability assessments. The process would take years. Westbrook had months before the next winter. He went around them. He contacted industrial clients directly. Factories, warehouses, hospitals. Institutions with their own water systems, not subject to municipal codes. He offered free installation and free solution in exchange for documented performance data. By June 1934, he had 340 test sites across Illinois, Wisconsin, and Minnesota. He hired 2 chemists to help monitor the installations. He borrowed $8,000 from his brother to cover materials costs. Standard Oil refused to fund the project officially, but allowed him to continue as independent research. The winter of 1934-1935 was the real test. Westbrook's glycerol solution was installed in 340 buildings. He personally inspected 60 of them monthly, checking for corrosion, contamination, chemical degradation. The glycerol remained stable. Pipes showed no unusual corrosion beyond normal aging. Water quality tests revealed no contamination, and freeze failures remained at 0. Not one treated building reported a burst pipe. The control group, buildings using traditional heat-only protection, reported an average of 11.4 failures per building over the winter. Insurance companies began offering premium discounts for buildings using glycerol antifreeze. 5% off annual property insurance for documented installation. The economic argument became overwhelming. A building spending $200 annually on extra heating to prevent freezing could instead spend $80 on glycerol solution and save 5% on a $3,000 insurance premium. Net savings, $270 per year. Payback was immediate. By spring 1935, demand for glycerol antifreeze exceeded Westbrook's production capacity. He partnered with Procter & Gamble, a major soap manufacturer with excess glycerol production. They formulated a standardized product, 75% pharmaceutical-grade glycerol, 24% water, 1% corrosion inhibitors, and biological preservatives. Retail price, $2.40 per gallon, enough to treat 400 feet of standard residential piping. The product launched in September 1935 under the brand name Winter Safe. By November, it was sold in hardware stores across 22 states. By December, it was sold out everywhere, north of the Mason-Dixon line. The municipal building codes remained a problem. Cities refused to amend regulations allowing antifreeze in potable water systems, despite overwhelming evidence of safety and effectiveness. Westbrook's solution remained legal only in private industrial installations. Residential use existed in a gray area, not explicitly prohibited, but not officially approved. Homeowners installed it anyway. Building inspectors couldn't prevent homeowners from adding chemicals to their own water systems. By 1937, an estimated 400,000 residential buildings used glycerol antifreeze despite lacking code approval. The regulatory breakthrough came in 1938. The American Society of Mechanical Engineers published comprehensive corrosion studies on glycerol water mixtures in various pipe materials. 5-year exposure tests showed no accelerated corrosion compared to plain water. The American Water Works Association certified pharmaceutical-grade glycerol as safe for potable water systems at concentrations up to 80%. The American Medical Association confirmed non-toxicity at typical concentrations. Armed with these endorsements, Westbrook petitioned Chicago's building department for code amendment. They approved it in March 1938, making Chicago the first major city to officially permit antifreeze in residential plumbing. 43 other cities adopted similar amendments within 12 months. By 1940, glycerol-based pipe antifreeze was standard practice in northern construction. Building codes required it in exposed pipe sections. Insurance companies mandated it for coverage. The winter burst pipe crisis that had plagued cold climates for a century was effectively solved. Westbrook's insane solution had become conventional wisdom in 6 years. Property damage from frozen pipes dropped 89% nationwide between 1934 and 19. Insurance industry estimates credited Westbrook's invention with saving $40 million annually in prevented damage. He received royalties from Procter & Gamble's Winter Safe sales. By 1942, those royalties totaled $1.3 million. He donated most of it to engineering scholarships at MIT. The long-term impact extended beyond frozen pipes. Westbrook's work established the principle of chemical intervention in building systems, using additives to solve structural problems. The same approach led to corrosion inhibitors in boilers, scale preventers in water heaters, biological controls in cooling towers. His methodology of rigorous field testing before regulatory approval became the model for building product certification, and his business model of partnering with industrial waste producers to create valuable products pioneered what would later be called upcycling. Soap manufacturers had been paying to dispose of glycerol. Westbrook turned waste into a $40 million annual industry. Westbrook left Standard Oil in 1941 to focus on chemical engineering consulting. He worked on wartime fuel stabilization, post-war plastics development, eventually specialized in water treatment systems. He died in 1968 at age 68. His obituary mentioned his contributions to petroleum chemistry, his wartime service, his work in water purification. One paragraph mentioned Winter Safe, the pipe antifreeze that had made him wealthy and saved billions in property damage. The engineering community remembered differently. The American Society of Mechanical Engineers awarded him their Distinguished Service Award posthumously in 1970. Specifically citing his frozen pipe solution as the most significant contribution to cold climate construction in the 20th century. The glycerol-based antifreeze formulation Westbrook developed in 1933 is still used today. largely unchanged except for modern corrosion inhibitors and biological preservatives. Every building in cold climates relies on the same principle he proved in the Palmer House basement in January 1934. You can't fight freezing with heat alone, but you can prevent freezing with chemistry. Scientists called his solution insane because it violated the accepted approach of heating everything. Westbrook proved that sometimes the insane solution is the one that actually works. Winter never broke a pipe the same way again. If this story moved you, please like and subscribe. Tell us in the comments where you're watching from.